Hi everyone, in this video we'll try to cover the concept of chapter 8, electromagnetic induction. Let's start with the given provided with this exercise. A metallic rigid rod Mn of mass 0.25 kilogram can slide without friction on two parallel and horizontal metallic rails PP prime and QQ prime. During sliding, the rod remains perpendicular to the rails. These two rails separated by a distance L are connected by a resistor of resistance R. Neglect the resistance of the rod and of the rails. So as you can see here on this figure, the part P to P prime and Q to Q prime shows the path of the motion of the rod Mn along these two rails. And they said that the mass of this rod is 0.25 kilogram. The distance between these two rails is L, and they are connected across a resistor of resistance R. We neglected all the resistive forces of the rod and the rails. Let's start with part A, electromagnetic induction. The whole setup is placed in an upward, uniform and vertical magnetic field B of value B. So here this figure represents a horizontal figure and the magnetic field B is vertical. So the angle between B and the rod, or B and this figure at all, will be 90 degrees. The position of G, the center of inertia of the rod, so this is G, is defined by its abscissa axis on the horizontal axis, OI, with O corresponding to the position of G at T0. So at T0, the main or the origin of this rod is at point O, which is at the distance D from O prime. At an instant T, G has an abscissa OG axis and a velocity V of algebraic value V. So as you can see here, the motion of this rod is to the right side from P to P prime, or from Q to Q prime. Let's start with the first part, part 1. Show that taking into consideration the arbitrary positive direction chosen in figure 1, the expression of the magnetic flux crossing the surface limited by the circuit MNPQ given in this shape. So first part, part 1, we must prove that the flux equals to B D plus X L. We must prove this one. So this one to be proved. How can we start? We will start from the main formula. The main formula for the flux says that the flux equal N. We can just write the main formula with the vector forms, which is N multiplied by B vector dot N small n vector multiplied by the surface area S, or we can just go for the final magnitude formula, which is N B S cosine the angle between B and small n. Since this circuit is represented of one loop, so n here is going to be 1, and the magnetic field B will remain B. The area S, which is the surface area of the PNMQ shape. So the area of this one, which is the length multiplied by the width is L, and the length will be D plus X. So the total length will be D plus X, and the width will be L. So here we can just go and write, instead of S, D plus X multiplied by L cosine the angle between B and N. As you can see here, N is upward, vertical upward, B is vertically upward, so both of them will have the same sign, the same direction, and the angle will be 0. So cosine 0 will give us, this one is 1, so the answer will be B multiplied by D plus X L. Just take into consideration, if they didn't provide you the sense of N or the direction of N, you must use the positive sense here. Just go and take your four fingers along the same direction as shown on the figure, starting from Q to M to N to P, the four fingers will be pointing towards the positive sense. Your thumb will be pointing upwards along the same direction as B. And now you can prove that the cosine of 0 will be 1, and number 1 is proved. Done. Number 2. In number 2, they said derive the expression of the induced EMF across the terminals of the rod MN in terms of B, L, and V. So we must find E as a function of B, L, and V. How can we start with this one? We can just go and search for the formula of E. E is minus d flux by dt, which is the derivative of this expression, which is the derivative of B multiplied by d plus x and L by dt. As you can see, now we can just take all the constants outwards and leave the variables inside. So B, the magnetic field, will be constant, so we can take it out of the derivative. L is constant, so we can just keep it out. And then here the remaining is derivative of, let me change the color for d plus x by dt. So the derivative of d plus x, d is constant, so it's going to be 0, and the remaining function will be b L. Now I'll just take the derivative of this one, and it will be the derivative of x will be x prime or v. Don't forget to write all the negative sign outward, so just keep the negative sign. The answer will be minus BLV, and it's done. Part 3, or sorry, this is part A. Now we'll just go to write part B. So this is 2A, and now we'll move to part B, derive the expression of the induced current. So let's try to go here and write I equal question mark, the expression of the induced current, not the value, in the circuit in terms of R, L, B, and V. R, L, B, and V, in terms of R, L, B, and V. How can we write this one? Usually, if we just go and take a recap for the calculation of the current, or for the formula how to find the current, usually we can, if we just go and search for the current across a resistor, we can use Ohm's law, U equal Ri. So we can just go and write I equal U over R. In this circuit, they didn't say anything related to the internal resistance of the rod. So if we go and search again, we can say that it's sliding without friction, metallic parts, etc. The rod remains perpendicular. They didn't say anything about the internal resistor. This is an external resistor related to the circuit. It's not about the rod. But here they said one sentence, which is neglect the resistance of the rod and of the rails. So the rod, the small r of the rod is neglected. So we just care for the capital on this circuit. And in general, the voltage here will be equal to R times I in this circuit as a whole. So to find I, we can just go and write E equals R times I. The voltage will be the same, so I will be equal to E over R. This is totally similar to Ohm's law. So if you are just thinking about how we did this, Ohm's law says the voltage across an resistor is Ri. Here in this circuit, this is a resistor. So the voltage between the rod, between points M and N, which is the rod, will be equal to the voltage across the resistor R. So the voltage here is E, and the voltage here will be R times I. Then we can just go and write I equal E over R. Now substituting the value of E, we know that E equals to minus BLV in the previous part. So minus BLV over R. And that's the expression of I. What can we say about the negative sign of this current? We'll comment on this one in the next part. Look here, they said here in part B or B to I, deduce the direction of the induced current. We must find I. So this is part I, this is part 2I in B. So what can we say about the direction of the induced current? Usually we can do this in two ways. The first way, which is easy, go and search for Lenz's law, apply Lenz's law, and you will see if it's going to be moving clockwise or counterclockwise. But here, since they said deduce, so we must use the previous part. In the previous part, we found that I is negative. So since I is negative, then the direction of I is against the positive sense provided, or against the positive direction, we can say. Let me just make it small. So from the negative sense here, or the negative sign, we know that the direction of I, of the current I, is against the positive sense or the positive direction. Where is the positive direction? As you can see here, this is the positive direction. It's from Q to M to N to P. But I is just circulating in the opposite direction. Alright, let's move to the next part, part 3. Show that the expression of the electromagnetic force F acting on the rod can be written as this one. So let's try to copy paste this expression and try to seek for it. So A3. In general, the expression for F, or Laplace's law, Laplace's force, equals to I times L times B times sine the angle between L and B. So let's write sine theta, and let's go and search for, first of all, for the theta. So the current I, or the rod L, is horizontal in this way, B is upward, so the angle between L and B is 90 degrees. So this is the first one, which is sine 90. Which is 1. So the answer will be I L times B. Let's go and substitute the value of I, which is negative. So it's going to be minus B LV over R multiplied by LB. So it's going to be negative B square L square V over R. So after multiplication, we got this formula. In case we want to find the vector, then we can just go and add vectors, since they wrote here F as a vector form. Don't forget that the Laplace force is a vector, so it has a direction. So just we can write this one and finish it by writing F vector equals minus B square L square over R, and the vector form for F will be represented by a vector on the velocity. That's all for part A. We'll start with part B. Before starting with the second part, which is part B in the same exercise, let me just recap two ideas. The first idea, why we used I equal E over R. if we go back to the figure provided here, we said previously that if you want to apply the law of the voltage across the rod, we take the positive sense. So we start for U from M to N, and we write which is Ri minus E. This is the equation. Here there is no internal resistance, so it's going to be minus E. Similarly, if we just apply the same law for UMN, but now across the resistor, so applying UMN, but now we are just moving along this way towards the external resistance R. Since we are moving against the direction provided, so it's going to be negative. And Ohm's law says that it's going to be R times I. The voltage for UMN and UMN are equal, so it's going to be minus E equal minus Ri. So finally, I will be equal to E over R. For this reason, most of the time we can apply the equation for I equal E over R without going for all these steps. So it's correct to write I equal E over R directly and continue with the remaining values. The second idea that I want to take into account here for this part, why we used F as a vector and why it's negative, why it's not positive. If we go back also to the same figure, we can say according to Lenz's law, here the rod is moving to the right side. So Lenz's law says that the rod will try to apply or create a force. We call this force Laplace's force, which is going to oppose the causes. The cause here, which is the motion to the right side, so it's going to apply a force to the left side. So take your 3 fingers, the last 3 fingers to the left side direction. This is going to be the F. B is vertically upwards, so your first finger will be upwards and your thumb will be pointing towards yourself. So the current will be moving from N to M, to your side. In this way you can prove also that the current I is against the positive direction. So we can do this in 2 ways. Either using Lenz's law or the other way from proving that I is negative in expression BI. So I is negative here. So this proves that the current is against the provided direction. Now we can move to the, and that's just a comment here, F is negative V. So the velocity of the, or in general, F is negative against the motion provided. Let's move to part B. In part B, they said that we have 3 undamped oscillations. We remove the magnetic field B, so no more magnetic fields in this region. The center of inertia G of the rod is attached to a horizontal massless spring of unstretched length L0 equal D, as you can see on the figure. And the stiffness is K equal 50 Newton per meter. Thus, at equilibrium, the abscess of G is X equal 0. So, at equilibrium, the abscess of G is X equal 0. The rod is displaced by a distance xm equal 10 centimeters. So initially we displaced the rod by 10 centimeters in the positive direction to the right side, and is then released without initial velocity force. So V0 at T0 is 0. So let's write a given. We'll use these givens later. At T0 equals 0, V0 is also equal to 0. And x0 will be equal to the capital Xm, which is 10 centimeters, or Xm. Okay. The rod thus oscillates around its equilibrium position at an instant t. G has an abscess x and velocity v. Let's start with the first part 1. Write in terms of m, v, x, k, and x the expression of the mechanical energy of the system. Take the horizontal plane as the reference. So we can just go and write the mechanical energy, ME, which is equal to KE plus PE. Here, the kinetic energy will be half mv square. Since we are taking the horizontal plane as the reference for the gravitational energy, so there is no gravitational energy, there is only elastic potential energy. So it's plus half K x square. And as you can see, we covered MVK and X in the expression. That's all part 1. Part 2. derive the differential equation of the second order in X, which describes the motion of G. They said previously that there is no friction forces acting on this motion or in this rod. So we can say that the mechanical energy ME is conserved, equal to constant. And now ME prime, which is the derivative of ME with respect to time, will be equal to 0. Implies that derive this expression and you will get half m into 2v v prime plus half k into 2x x prime. This is equal to 0. Cancel 2 with the half, it will be mv v prime plus kx x prime equal to 0. Now we can just remember that v prime is equal to x double prime, and we can just go and write the values m v x double prime plus, we can continue with the other part, which is k x. Concerning x prime here, forget about this arrow, x prime, which is v, and it's equal to 0. Now we can take v as constant common, it will be mx double prime plus kx equal to 0. Sure, the velocity is different than 0, then the expression will be m x double prime plus kx equals to 0 divided by m, and the result will be x double prime plus k over mx equals to 0. That's the answer. So once they ask for a differential equation, that's what you have to do. The last part, the solution of this differential equation is of the form x equal a cosine omega t plus phi. Determine the values omega a phi. They showed here that a is positive constant. Sure, here a usually is the maximum displacement. We usually write the expression for the solution as x equal xm cosine omega 0 t plus phi. So they just change it into a. Let's write the expression. So it's part 3, x equal a cosine omega t plus phi. We must search for a, for omega, and for phi. Usually prefer to find x prime, x double prime, substitute it in the solution, in the equation, differential equation, and then go and seek for the answers. So you must go and write x prime equal, a is constant, it will remain here, and if you just go and remember the math part, once we derive, we go clockwise. Once we integrate, we go anti-clockwise. So cosine will be changed into minus sign. And omega will be outside, so it's going to be x prime will be equal to minus omega a sine omega t plus phi. That's the first derivation. The second derivation, to find x double prime, sure, the sign will be cosine, or the minus sign will be minus cosine. It's the same if you take the minus with you or just go for the function. So here it's going to be minus cosine omega t plus phi. Omega will be omega squared. We just derived this one outside and multiplied by a. If we just go and substitute these values in the differential equation, you will just get this result. So instead of x double prime, we'll write minus omega square a cosine omega t plus phi plus k over m, the same a cosine omega t plus phi equals to 0. We can just take a cosine omega t plus phi as a common, and here it will remain minus omega square a, sorry, without a, plus k over m equals to 0. Implies that, sure, this one is not equal to 0, so that's the result. We just write omega square equal k over m, implies that proved omega equal radical k over m, and k is given upwards in the question, it's 50, and the mass, they also gave us the mass in the previous part, which is 0.25. So we can just write the answers, the part, and you will get an answer which is 14.1. The unit for omega is radian per second. It's similar to the frequency. In frequency it's per second, which is hertz. Here it's radian per second. Let's now move to the second unknown. So we just here in the first part we got omega. We just go for A and for phi right now. We must use the initial conditions. So we just go for the first line here. We'll take a screenshot for all this line. It's important. And we'll be using this line downwards in the solution. So let's go here. So we know now that the velocity initially is 0. So if we go for the x prime, which is minus omega a sine omega t plus phi, this one is v, so x prime it's v, so 0 equals to minus omega a sine, we are just substituting t as t0, so this one is 0 plus phi, so 0 equals to minus omega a sine phi. If we want to find the answer for this one, initially the speed is 0, then a and omega are different than 0. We can say that sine phi must be equal to 0, so phi must be equal either 0 or phi must be equal to pi. Why is that? Just note that cosine 0 is 1 and sine 0 is 0. So here the answer, in order to be the answer 0 in the left side, sine phi must be equal to 0, or sine pi is also 0. So the answer of phi must be either pi or 0. We'll choose one of them after a while. The second idea is that x is equal to xm at t0. So we'll just go and write the expression of x, which is this one, a cosine omega t plus phi, a cosine omega t plus phi, and right here x, instead of x it's going to be xm 10 centimeters equals to a cosine omega 0 t, so this one is 0 plus phi. Sure, a here must be positive value. They said that a is positive, so this one will be, phi has two choices, either 0 or pi. Pi will give cosine pi it's minus 1, so this one will be 0. Implies that phi must be equal to 0, and we can just say that a will be equal to 10 centimeters. Okay, now we'll finish with the last part, which is part C, free damped oscillations. The setup of figure 2 is placed now in the magnetic field B. The rod is displaced again by xm equal 10 centimeters in the positive direction, and it's then released without initial velocity at t0. The rod thus oscillates around its equilibrium position at an instant t. G has an abscissa x and velocity v. Let's start with the first part, part 1. Calculate at the instant t0 the mechanical energy of the rod or of the system. We must take the horizontal plane as the reference. So if we want to find the mechanical energy, which is half mv square plus half kx square, knowing that there is no height, so half mv square, initially it starts from rest, so there is no speed, but there is elastic potential energy, so me will be equal to half kx square. K is 50, as we can remember, and the initial distance, which is 10, it's going to be 0.01 squared. And now after calculation you will get the answer for this part. Knowing that in such equation, be sure to write the expression of the whole expression of the mechanical energy. So I mean by that, don't forget to write Ke plus Pe, so kinetic energy plus potential energy, and here just say that it's going to be elastic potential energy. The speed is 0 since initially it starts from rest, so the remaining part will be half times the K, which is 50, times 0.01, and the result will be 0.0025 joules. Okay, note that the units must be, this one must be in Newton per meter and this one in meter. Okay, in the second part, part 2a, during its motion the oscillator loses mechanical energy. Show that the power of the electromagnetic force F exerted on the rod is given by this expression. So the power of any force, it's the force times the velocity vector, and the force here, we know the force from the previous part, which is somehow, let's go a little bit backwards. Okay, here is the F, which is the negative B square L square V over R. So this is the force times the velocity, so it's multiplied by V. Sure, here we must get B square L square V square over R. That's the result. Okay, note that here, once we want to find the power, which is the velocity vector multiplied by the force vector, and it's a dot product. So once we substitute F, which is minus B square L square V over R, multiplied by velocity vector, which is the V, dot product is cosine, so it's going to be F times V times cosine the angle. The force is backwards, the velocity is forward, so the angle is 180, which is minus 1. The result will be plus B square L square V square over R. Next, part B, determine the expression of the power lost in Joule's effect in this resistor. So in any resistor, the power lost will be equal to the Ri square. We keep R, and the I, which is equal to the, let's go backwards and copy the value of I, which is the fraction form. Here is it. Let's take it. Okay, so now we can just go and write minus BLV over R. It's square, so it's going to be R over R will cancel. We got just BLV square, square over R. So it's going to be B square L square V square over R. As you can see, the power and the lost energy, it's the same. Let's go to the part C. In part C, reduce in what form of energy the energy of the oscillator is dissipated. As you can see, all the energy provided by the force is lost in heat as a heat energy in the resistor. So in part C, we can just say the power of the energy lost as thermal energy due to Joule's effect will be equal to the power provided by the Laplace force. Therefore, the mechanical energy is transformed into heat energy in this resistor, so nothing is used here. In the last part, after a few oscillations, the rod stops. Give in joules the value of the total energy dissipated by the oscillator during its motion. If we go backwards for a previous part here, let me just highlight it, 0.0025. This is the initial energy provided by the rod once we displaced the rod.
So in the last part, part 3, all the energy, which is equal to ME0, 0.0025 joules, this is the total energy dissipated as heat. That's all for this exercise. If you have any question, just write a note and I'll see you in the next lecture. Thank you.